Welcome back. We have another max power transfer problem with a lot of extra fun stuff in it. Here's our circuit. $200-volt independent source, 25 ohm up here, 10 ohm here, 100 ohm here, 20 ohm here, and a dependent source given by 30 I delta, where I delta is this reference voltage through the 10 ohm resistor. I'm sorry, reference current through the 10 ohm resistor. Then there's terminals A, B here that we're going to connect a load. We're going to call that R0, and it's a variable resistor, so they put an arrow through that to indicate a variable resistor. So we're asked to find R0 for max power transfer. All right. So when you see these maximum power transfer problems, it means you need to find the Thevenin equivalent. So and remember, there's two steps to find the Thevenin equivalent. There's one, find V sub Thevenin, and two, find R sub Thevenin. Now we're going to do, mesh current and node voltage, but we're also going to do some source transformations. And then in the end, we're going to have this big quadratic thing that we got to mess with. So there's a lot of fun on this guy. All kinds of interesting things. So let's do step one. We're trying to find V sub Thevenin. So V sub Thevenin is the open circuit voltage. That means the load is removed when you calculate for V sub Thevenin. So this R0 is the load. You're going to take that out of there. But just for some fun and to show that there's some different methods. I mean, you could use node voltage right now. There's two nodes, right? There's this node and this node. If you remove this, you could do that, and we've done that in the past. But just to have some fun, and to show that there's a variety of other methods, So for fun, let's do some source transform, to simplify this guy. So so if you here, I don't want to, in the interest of time, I'm going to do this a little bit quicker. So first you're going to get this guy. You're going to move the 25 ohm to over here. All right, move this guy. I'll draw it kind of tiny here, and then don't forget to remove the load. So you're going to do that. That is, do a source transform on these two guys and replace it with a current and move the 25. Then you can do a parallel simplification, and so you'll end up with, well, here I'll draw it one more. I'll just keep drawing it. You'll end up with an equivalent resistor right here, and then the 100, then the 10 ohm, then the this guy, and then the diamond. Right? Add these two together in parallel simplification. You end up with that, and then you can do a source transform back to, so this is going to be A, this is going to be B, then C. You can do a source transform back to a voltage source, and you move the resistor, and then the 10 guy will be here, and then this guy will be here. And then you can add these two resistors, and you'll get, the final thing you'll get with values is going to be a 160 volt. And I need to draw it a little bit bigger here. I'm kind of running out of room. And then a 30 ohm. And then the 20 ohm is still here. And the 30 I delta. You end up with this. Okay, so after 1, 2, 3 manipulations, you can get this. First do a source transform from, voltage in series with a resistor to a current source in parallel with a resistor, and then combine these two parallel resistors to get this. Then you can do another source transform back from current in parallel with a resistor to voltage in series with a resistor, and then you can add these two guys and you'll get this. So this is a little bit simpler than the original circuit, and it should still behave the same with respect to terminals A, B. We haven't changed anything that's kind of between A, B. We have these two guys between A, B, and then we have an equivalent two elements that behaves the same as all of these other guys that were between A, B. So as far as what's between A and B, it behaves the same. Okay, as far as like what's between, like across here, it behaves different because this thing's totally gone now. But in terms of what's between A and B, it behaves the same. All right. And along those same lines, I delta is into node A. I delta is the current into node A. That's still here. So this is still I delta. Once again, from the perspective of AB, this is I delta. I delta is the current into node A. So at this point, you might be tempted what to do. Well, you could use node voltage and you could solve for the voltage at this terminal. That would work, and we've done that before. You would just have one node voltage equation, and you could do that. But just to show you that you could do other things as well, you could also use mesh current. So let's do that. Let's do a little mesh current thing. So this is I delta mesh, which happens to be the same as I delta, this I delta right here. All right, so we're doing mesh current here for I delta. And kind of the reason we're doing that, to jump ahead a little bit, is that if we had I delta, we could get this voltage drop across here, and then we could get this voltage here, because this guy's dependent on I delta. It's 30 I delta. So, that's why we're solving for I delta. Okay, so we have coming into the negative terminal on this guy, we have minus 160. And then we have 30 I delta, that's the voltage across this guy. And then we have 20 I delta, that's the voltage across this guy. These two are by Ohm's law, right? Ohm's law. And then we have another 30 I delta, but this one's because it's a dependent source given by 30 I delta. So these sum to 0. So we just did the voltages going around the loop. There's only one unknown in here, and it's going to work out that I delta is 2 amps. And if we have this amps, the 2 amps going through this guy, we can calculate the voltage drop across here and the voltage drop across here. So let me redraw it just so that it's a little bit, clearer, kind of, maybe, hopefully. Here's what's going on between branches A and B. You've got a voltage drop here, which is 20 I delta by Ohm's law. And then you've got a voltage drop here, which is 30 I delta, because it's a dependent source. So the total voltage, which is the open circuit voltage across here, is V-Thevenin, across there is V-Thevenin, is just 20 I delta plus 30 I delta. It's just 20 times 2 plus 30 times 2, which is what? It's 100, right? 40 and 60, it's 100. That's V-Thevenin. Okay, so that's the first step here, is calculate the Thevenin resistance. And I took a little roundabout way just to play around with the different methodologies that we have. Do some source transforms. Then you could use mesh current. In the past we've used node voltage, but mesh current works, and then you get this. All right, that was process 1, to find V-Thevenin. Process 1. Let's do process 2. We're going to find R Thevenin. And what do you want to do here? So we have a couple choices. Back on our original circuit, we have a dependent source. So that means we have two methods available. We have test source method and we have I sub short circuit or short circuit method. Let's use, let's use test source method. So via test source, just for no particular reason, just because I think we've used short circuit in other examples. So just a little review of test source method. You're going to have your terminals of interest. You're going to hook up this guy right here, V sub test, and there will be a current associated with that I sub test, right? So you hook up V sub test, which is a voltage supply, and there's going to be a current induced with that. And these guys will vary by R sub Thevenin. It's may not be totally obvious that that's what happens, but they will. And these things will maintain the ratio of R sub Thevenin as they vary. So that means we don't really need to solve for an individual one of these values, because the ratio of these two values will maintain R sub Thevenin. Now, we saw that way back in chapter 2 when we had those tables of values, right? We applied various voltages to a circuit and we got currents, and that gave us the R sub Thevenin, remember? So that's kind of where this methodology comes from. Okay, so we go back to our original circuit here and we remove the load and we replace it with this test guy. So I'll redraw that. I'll draw that over here. So we have V sub test that we've hooked up between terminals A and B, and there's going to be this I sub test. Hope I didn't say. Yeah, I got T there. And then the rest of the circuit is in here. We've still got our diamond and our other guy, and then we've got this guy, and then we've got this guy, and then so test source method, you still open the I's and short the V's. Don't get confused with that with the short circuit method where you leave these guys. Okay, but in this guy this 20 ohm the 200 volt, this 200 volt guy, you short the V's. So this guy, I'm just going to draw a circle and replace him with a wire, which is a short circuit, and the rest of the stuff hangs out. Now after you do these replacements, in this case we did a short, you have to look and see if there's any effects on the circuit, and in this case there isn't, because there's still two resistive branches here. Now if this resistor weren't here, like in the original circuit, if this resistor weren't in the original circuit, then we'd be shorting out across a resistor, which would eliminate this second one as well. Okay, but here we still have resistive branches here, so they stay. So you need to think about these kinds of effects of the changes. There's the changes themselves, the shorting part, and then sometimes there can be effects of that depending on the arrangement of the devices. Anyway, here's all these guys. This is still node A, and it still has our reference current I delta in it, which is driving this dude over here, 30 I delta, and there's a 20 ohm is still there, and 100 ohm, 25 ohm. I got all this stuff. 10 ohm, I got all that stuff. That's everything, right? Okay, so we need to solve for the ratio I test over V test. Did I say that right? R Thevenin is given by V test over I test. Hope I said that right the first time. That's what we need. We need this ratio. We don't need the individual values, but we need the ratio. As the values change, they will maintain this constant quantity here. Okay, so what should I do? Well, node voltage comes to mind, or mesh current comes to mind. We used mesh current over here. What would happen if we did node voltage? Let's just see. So we have two nodes. Well, what would happen if we had one node? This 25 and the 100, it looks to me like it's just going to complicate things. So let's just take the time and simplify this thing. basically we have a 100 in parallel with a 25, which is going, these two are in parallel. Those would simplify down to 20 ohms. And let's just go ahead and redraw this guy with a 20 ohm resistor. So we'll have one node voltage equation. That's the effect of that thing. The 10 ohm is going to be here, which we could actually could get rid of that guy too. We sure could. But let's not. Let's go ahead and leave it. So this thing between nodes, oh, let's call it node C and node B. Between node C and node B, these two guys simplified into the 20 guys, and here he is down here. And the rest of the stuff is the same. Oh, I'm getting a little squishy. I gotta draw bigger. Sorry about that. It's kind of squishy. Got a little squished into the corner there. I hope we'll be all right on that, I think. Anyway, we just have one node that would work, and I could simplify this into 30. You know, these two guys, and then it would be even simpler. But let's just do node voltage equation at A. So what are we doing? We're doing node voltage. What does node voltage do? It's sum of the currents. So the currents are going to be I, and then they're going to be V over R. Okay, so I need expressions for all of these currents coming into this node in terms of either I's or V over R terms. So I've got this I sub t, and that's fine because in the end I just want V sub t and I sub t terms floating around in my math because I'm trying to solve for the ratio of these two guys. So IT is fine. We'll just leave that. I need a couple other currents. So this is still I delta. I need the current through this guy. I need an expression for that. This guy here, let's call that, well, at this node here is V sub t. The voltage at that node is V sub t. And the voltage at this node is 30 I delta, if you use node voltage method. This is 30 I delta. The voltage at this point is 30 I delta, and the voltage at this point is V sub test, right? Because here we're starting at 0 and we're rising across this device by 30 I delta, because that's what that device does. It supplies 30 I delta volts. And then for this node up here, we're starting at 0 and we're rising from up VT volts by this test source. So this node the voltage at this node is VT, and the voltage at this node is 30 I delta. So the difference is VT minus 30 I delta. And by Ohm's law, you divide by the 20 ohms and you've got the current. Okay, that's the current expression for this, or the expression for this current. In terms of VT and I delta is going to be a problem, but so we need an expression for I delta, and if you look, here's node A, here's node B, and V sub t is the voltage across nodes A and B. So really, it's positive at A and negative at B. So across these two resistors over here is VT. So the polarity, the positive polarity, would push the current in the opposite direction from what our reference is. So I delta is basically, it's minus VT over 10 plus 20. And so the negative is because we're correcting for our reference, basically, for our reference current. Because the actual current, if you say, whatever that means, or the actual current, the current induced by this polarity here is going to be opposite of this arrow right here. So we need to adjust for that by putting a negative sign in there. All right, I can sum the currents at node A now. That is, I can write the node voltage equation for node A. So in is negative and out is positive. So I've got I delta going in, so that's negative, and the quantity for I delta is Vt over 30, which is Vt over 30. And that's going in here into node A, and then I've got IT going in, and then coming out I've got this guy coming out of node A, and that's given by Vt minus 30 I delta, which is minus Vt over 30 over 20. Those sum to 0. Whew. Yeah, that's it. It's ugly, but there it is. And all we got to do is pull out an expression of we need to make this guy look like Vt over It, which, believe it or not, we can do. So let's see. So make it look, like Vt over It. I'm just trying to document the thing here, So let's do that. So we'll take this It and put it on the other side. So It equals, and then so we put that over there, really, and then this guy becomes just, the minuses cancel, and this thing over here is I'm just gonna copy it down. Did I even do that? Is that right? Yeah, that's okay, right? So what is that? This is going to be, I'll put it over here. This is going to be Vt over 30 plus Vt over 20. Plus, let's see, the minuses cancel and the 30s cancel. And you just end up with Vt over 20. And so that's Vt over 30 plus 2 Vt over 20s, which is Vt over 30 plus Vt over 10, which is, you could factor out the Vt, and 1 over 30 plus 1 over 10. So that was all It. So It over, or rather we want Vt over, Vt over It. Vt over It is, so this, yeah, so what? So it's a little easier if you go another step. So Vt over It is 130 plus 110, which is 430 is, you multiply 3 times 3, 1/30 and 3/30 is 4/30, which is 2/15. So Vt over It is 15 over 2, which is 7.5, and that's our Thevenin. It's, yeah. So it's pretty ugly, but anyway, that's the process. So what have we done? We found V Thevenin way the heck back here, and we found R Thevenin way back here by a variety of methods and a lot of fun and a lot of math. Okay, now where are we? So the Thevenin equivalent, we have that. Let's just draw that. So we it's right here, right? So this is, what is this guy? This is 100 volts. This is V sub Thevenin. And then you've got a 7.5 ohm resistor, which is R sub Thevenin. Okay, and that's what we, so now we've got the Thevenin equivalent. Here it is. Yay. Now what we're going to do is we're going to throw this guy in here. We're going to throw the R sub 0 variable resistor in there. And, oh, hey, you know what? Oh, yeah. That's what we're trying to find, but that's the wrong thing. We actually want to find the not the maximum power transfer, but power to R sub O equals 250 watts. It would be too easy to, I mean, you know, we don't want to make this an easy problem, but it would be too easy just to find the maximum power transfer. What would that be? The maximum power transfer would just be when R sub 0 is 7.5 watts. And then you could solve for the current or the voltage and calculate the power in here. But we don't want that. We want 250 watts. So when does that happen? Let's just look ahead a little bit and what this thing's going to look like. We know that the maximum power transfer curve looks like this. So there's one value at the max, and that happens. So this is R sub 0 versus the power in R sub 0. And the maximum value, the power R0 max, happens when R0 is equal to R sub Thevenin. So it would happen at 7.5 ohms. Now they're not asking us to solve for the maximum value. They're asking us to solve for some other value, although I guess you don't know that right now. But if you solve for this, if you solve for the maximum power transfer, you'd find out that it's higher. In fact, I solved for that already somewhere. Now it turns out it's higher. Here, I'll tell you what it is. It turns out it's 334 watts. So I solved for that just by setting this equal to 7.5, calculating the voltage, which should be 50 volts, and then using V squared over R, or 50 volts squared over 7.5 ohms should give you 334 watts. So I did that already, but that's not what they're asking for. They're asking for 250 watts, which is somewhere in here somewhere. So 250 watts. So there's going to be two values. Okay, so basically we're going to kind of derive the expression for maximum power transfer as a function of the load resistance. We're going to do that right now. So we have a current going through this thing, right? Let's call it I. And I, by Ohm's law, I is V over R. So it's going to be 100 over the total resistance, right, which is 7.5 plus R0. Okay, and the power in R0 is the current through I0 times R0. So you can take this guy and plug it in here, right, and you're going to get 100 over 7.5 plus R0 squared R0. That's basically this plot. Okay, so the question is asking what resistor value, what R0 value will give you this 250 watts. So what we're going to do is we're going to set, this thing, the expression for the power in R0, set it equal to 250 watts and solve that. Okay, so what I did up here was basically, this thing right here is basically this is the derivation of, the max power curve. Kind of that's in the text. Anyway, this is the equation we need to solve, because this is the equation for power as a function of load resistor. So the rest of this fun is just solving this thing. So we'll so 100 squared is 10,000, and then the bottom squared gives you R0 squared plus 15 R0 plus 7.5 squared, which is 56.25, all times R0. That's equal to 250. So we're solving here. We can rearrange this thing. So 10,000 R0 over 250 is the rest of the stuff, R0 squared plus 15 R0 plus 56.25. And then 10,000 over 250 works out to 40 R0. Is R0 squared plus 15 R0 plus 56.25. And then you can move this guy over here, and you end up with R0 squared minus 25 R0 plus 56.25 equals 0. All right, this is a quadratic that we can solve, and we've got this quadratic formula here. We've got when you're given in a quadratic of the form ax squared plus bx plus c equals 0, that's a quadratic, right? Then we have this quadratic formula where x is given by minus b plus or minus root b squared minus 4ac over 2a. This is just the quadratic formula back from, math class somewhere. Quadratic formula. Okay. So A is 1, B is minus 25, C is 56.25 in this formula, and X is R0. So basically R0 is minus B, which would be 25, plus or minus root B squared, which is 25, minus 4 times A is 1 times 56.25 is over 2 times 1. So it's basically 25 plus or minus 20 over 2. So R0 is you expect a 2.5 and 22.5. So that's these two values right in here. This is 2.5 ohms, and this is 22.5 ohms. That's the answer. All right. Got a little sunlight coming in the window. All right, hope that was useful. See you next time.